Welcome back. This is Clinton. We're discussing the final project for CSC 535 at University of Illinois at Springfield for the spring semester 2024. In this project, I am building a convolutional neural network to recognize images of latches with different kinds of locks or potentially no lock. In the last video, I discussed my model builder function that starts with a signal that is the image. It transforms the signal in various ways and produces an output where the output is a number between 0 and 4 corresponding to one of the 5 models, one of the 5 classes, corresponding to one of the type of locks. Now we're going to talk about building some models. Maybe. We might be hung up here. Yeah, we're going to have to restart the kernel. For whatever reason, it looks like when you, if you import a Python script and then you change it, you have to restart your kernel to capture the change. You can't just do the import. You can't just repeat the import. You have to actually restart your kernel. And so this is the part that I needed to do that for. So we build our basic model. This is with the default values as indicated here. The basic model has just under 21,000 trainable parameters. Most in this convolutional layer. A good number in the preeminent dense layer. Maybe less than you might expect. Okay, so that gives us information about our baseline model, which is just using default values for the arguments. So we already trained. Now this might be a little bit different from what we'd get if we compiled the model now. This model and training was done previously. There have been some changes that I've made to the code. I might run it again with the changes, but if I do, then it's not gonna, then these learning curves and whatnot may not, they may change. So this is this should not be anything new. This was all covered already in previous videos. This is a little bit new. We've covered it in the class already, but the model has a method called fit, which actually does the training. That's how you do the training of the model. The first argument is your training data set, which is obvious based on the code. The validation data is a named input, a named argument, and is our validation set. Number of epochs, that's the number of times that we're gonna pass. We're gonna pass every image in our training set. We're gonna pass every image through our model for training. We're gonna do that 150 times. Or up to 150 times. Verbose is a flag which indicates how much information you want to see. It's how much information you want to display while the training is ongoing. For whatever reason I chose 0. I would have chose 1 at this point. And so 0, it basically doesn't output anything. 1, it'll show for each epoch, it shows information. Shows a lot of information. It shows it shows the training loss and I think the accuracy after each batch, and then it'll show validation loss and accuracy after each epoch. So your batches, I think we said our batch size is 64, so that means each batch is going to be 64 images. So we'll see our training loss and accuracy after 64 images are passed through the training model, after the model is trained on 64 images. We'll see a training validation and training accuracy and loss. And then after all after all the images in the data set, so 366, I think that's correct. So after all 366 images are passed through the model for training, then you'll see validation, training, and loss. That's if we used verbose 1. If we used 2, interestingly, if I recall, using verbose equals 2, you actually get less information, if I recall correctly. I think it just spits out information once per epoch. Callbacks, I don't know how best to explain that. Callback is like a function that goes at certain points in the during the execution of this method. So it says it's like a function that gets called by a function. In the get early stopping we talked about earlier, this is used to end the training process early. In particular, if the validation loss does not reach a new best after 25 epochs. That's the default early stopping parameters. So this function call says, okay, pass the training images through the model, train the model on those images once, repeatedly, up to 150 times, but stop if the model's results do not improve 25 times in a row. So pass it in, check to see if the model has improved, and repeat either until you've either 150 times or until it stops improving 25 times in a row. And it's not simply, okay, so it's not considered improving unless it reaches a new best value, unless it is a new all-time best. I think what I just said is a very subtle and subtle distinction. Anyway, so once it's done all that training, we call our function that we defined earlier, and you can go back and listen to the video. Display learning curve. It will show how the training and validation loss changed throughout the training, and you can see that the training loss declined throughout. It was still declining. Now that's good. Training loss is the lower the better. The accuracy tends to be lower when the accuracy tends to be higher when the loss is lower. However, the validation loss seems to have kind of bumped up and bumped around, but aside from just at the beginning, it trended upwards. And you can see it spiked at the very end, but that it probably would have come back down, and who knows. What do we call this is overfitting, because the validation loss is trending up, and while the training loss is trending down. Training loss is getting the model is getting better is improving on the training set and is getting worse over time on the validation set. So we call that overfitting. This means that the model is memorizing the training set rather than learning anything about latches in general. It's learning about the images in particular, those particular images. All right. Yeah, so it's learning details that will not tell it that will not lend itself, it will not generalize to other examples. So here I I looked up the accuracy and validation accuracy at the last epoch. You can see the training accuracy was 76%. The validation accuracy was 41%. I'm not going to go into these numbers through all of. I'm not going to keep doing that. But we see this is important. The evaluate function. It's a method of a model, and it basically will predict the label of each image in the data set that you pass it. It will predict each image, and it'll give you information about what it did. So the accuracy of this model. So the thing that I may have forgotten to explain or didn't explain. So this history information, I'm getting the results from the last epoch. Now, that's not the same thing as that information is not the same as the model. The history, the history and the model are I'm not saying that very well, but when you look up the history, you're seeing how the model performed during the last epoch. When you query the model to evaluate or make predictions, you are seeing based on the epoch where it performed the best on the validation set. If we hadn't used a validation set, then it would be the best it would be the version of the model that performed best on the training set. But in any case, so that's why there's a difference. When you look up the accuracy and validation accuracy in the last epoch, you get 76 and 41-ish, 41.5%. Whereas if you evaluate, you're going to get about 40% for both. That means before the model started overfitting, when it was doing before the model started overfitting, it was doing about the same accuracy on both sets, both the training and validation set. And that's more or less, that's pretty much what you expect. So if you use this baseline model, if you use it going forward, if we used it on the test set, then we would probably get about 40% accuracy. So that was the baseline. I think we can just keep going. The rest of this project is pretty should be pretty easy to explain. So here we're using now up here I'm defining some dictionaries. I don't need that. Can take that code right out. Down here, so the dictionaries are the keys for this dictionary that I created are the values that I'm using in these loops, and so I'm building a model in each iteration of the loop, and I'm getting the history for that model, and so I'm saving that in this dictionary. I don't really need to do that. I never end up using that information. I never end up using that dictionary, so it's a waste of time. I'm not sure what I intended to do with that dictionary. Yeah, I don't know. But I could have used it. I could have used it in various ways. I could have used it to pick up the training from where I left off. I don't really recall why I didn't do that, because I end up starting over, just training. I end up training a model with the quote-unquote best parameters from I just start over with the same parameters, the produce the best model. And I don't recall why I did that, but I think that's the right thing. I think that's fine. I think having all of these models in a dictionary was a waste of memory. I think it was a waste of memory. So I think it is just and proper to get rid of that. Get rid of that dictionary. So here's the one time I did appropriately use the seed. I don't think I end up ever using this again. I should have. Maybe I'll try to do that if I remember it now. Going forward. So I have a loop. So each iteration of the loop, nested loop actually, I create a model with a certain number of convolutional layers and a certain number of filters in the first layer. Remember, the filters are the thing that zip, across the image, and in the first, just across the first row, the first line of the image, then the next, and the next, and the next. And for every pixel in the image, it produces a it produces a value based on the values in the image around that pixel. So let's see. So we have a nested loop with the convolutional layer and the number of filters in the first layer. So what we're doing here is we're trying to figure out the number of layers and the filter count for which we get the best model. We get the model that produces the lowest amount of loss, validation loss, I believe. Although I don't use an early stopping at this stage. So I was trying to find. My goal at this stage was to find a model that had the minimum training loss, and then try to regularize the model later on. And that didn't really work. I think I have some errors that I need to address. I think made some mistakes that I needed to address to improve my generalization efforts. But at this stage, I was trying to find the model with the lowest training loss. That was my goal. So we use between 2 and up to 4 layer counts, and we use 2 to the 4th, so 16, 30, or 32, or 64, or 128 filters in the first layer. We build a model, we train a model, we look at the learning curve. And, I'm not going to get into it because, like I said, I'm not going to keep talking about the data. That's in the report. Okay. So that's a search. Once we found the best quote-unquote model, we then looked at model information. So here we see like 392,000 trainable parameters. And so we're calling this tune filter model. This is the best model from the tuning filters section. I don't know why I called it that. I suppose tuning layer and filter count. That's fine. Whatever. So we could have called it tune convo history and tune convo model. But so we use the same information, the same parameters, the same, I would call them parameters, hyperparameters, but we use the same ones from the best, from the tuning phase, the tuning, we use the parameters that produce the best model in that tuning efforts. And now we planned on training for 150 epochs. Okay, so it ran for 98 before it stopped early. So you remember we created the method for getting an early stopping object, and so it's going to have a patience of 25 by default, since we didn't pass an argument. So then this is the 98th epoch. Now this is a little bit confusing because each epoch kind of looks like, when you evaluate, it kind of looks like an epoch. So this is the 98th epoch right here, and then this actually I am confused. I'm not sure. Yeah, I think these are the evaluates. So the first one is evaluating on the train set. It's got 92% accuracy. Not sure why it's 0.3957 loss on the validation set. Well, I find that when you pass the same data into the same model, the numbers do seem to fluctuate a little bit. So, that's why the accuracy is a little bit lower than the last. The validation loss would revert back probably to like 73rd epoch. Yeah, probably that one. 2999 was the loss. Yeah, and then it never improved. So the model weights that we're looking at are actually from this epoch, where it achieved 89% on the test, on the train set, and 87 on the test, on the validation set. So it actually overperformed here. It actually overperformed what it did when it was training. I cannot account for that. And what I can do is put in the sorted lists. It's not really going to do anything. This should do something. So we're going to see in a moment that the validation, the heat map, the confusion matrix is not going to match. You see that the evaluation function shows an accuracy of 86+%. The accuracy according to the convolution matrix code shows 26%. So this is because this shows that the convolution, that the confusion matrix is broken. That code is broken. And so because of that, I did, probably not for the best, I did go ahead and display the confusion matrix with the model, model we tuned, the model that came out of the tuning phase, against the test data set. And you'll see the accuracy when you evaluate against the test data set is about 85%. And the accuracy when you draw the confusion matrix against the test set is also about 85%. So this is there is specifically a problem with the display confusion matrix that only affects train and validation. The code works fine for the test set. And that's why I think it's related to the ordering of the images. And I think that's caused by this flag right here, or the lack thereof in the training and validation data sets. So I've created these sorted? I don't know if that's right. That's the best word to use, because it makes it sound like I have manipulated the list in some way. I guess I think sorted is the right word, but it just doesn't sound right. So sorted means they're in the right order. They're in the correct order. Where shuffled, sorted versus shuffled. Shuffled means it's assorted. I don't know, it might be confusing. Maybe I'll find a better terminology. Okay. But you can see this is the confusion, the heat map. You can see that these are the true values of each. These are the predicted values. So this means there were 25 images of discus locks that were correctly identified as discus locks. There were 4 images of discus locks that were identified as padlocks, and there were 3 images of discus locks that were identified as zip tied. Now this is from, again, against the test data set. If I have time to reevaluate this notebook, I will correct that problem. I will I'll create a confusion matrix against the validation data set. The sorted validation data set. Okay. Isn't that a nice graphic though, that heat map? That is just lovely. Okay, next thing we did is we tuned the dense layers and dense the neurons in the dense layers. Now the So already I'm not actually using these dictionaries, not actually putting anything in them, and yet I still instantiated the dictionaries. Interesting. So this looks very, very similar to what we just did. I found that the best number of blocks, convolutional blocks, was 4. I found the best number of filters in the first layer to be 32. So I carried that over, I carried it over, and now we're gonna tune the number of dense layers and the number of neurons. As you may recall, whatever the number of neurons in the last layer, that's what we're tuning, and then the number in the previous layers will be double for each layer. So if there's 2 layers, the last layer is 16, then the preeminent layer the previous layer will have 32. And if there's a third layer, then the first layer will be 64, and then the next layer will be 32, and the last will be 16. Assuming 3 layers total, and the last layer being 16. So we're going to use up to from 0 to 2 dense layers. If you use 0, then obviously that means there are no dense layers. But of course, as a reminder, these dense layers are in addition to the dense output layer. So, we're not getting rid of that output layer. We are adding to it. So dense layers is 0 to 2. Then, those are the values we're going to test. And the number of neurons in the last layer will be between 16 and 64. So if you have 64 layers in the last, or 64 neurons in the last layer, and you have 2 layers, then that's a really narrow. That is a really narrow. That's really narrow testing. Okay. Wow. So if you have 2 layers, then you'll have 128 neurons in the first layer, and yeah, that is really narrow. I think I will test with 3. If I'm able to complete another run of this notebook, I will increase the max to 3. Maybe I did try a wider set of values, and maybe it crashed my maybe it crashed my kernel or something. I don't know. And you know what I forgot to do? Maybe there it is. Huh. Let's just do that. What I forgot to do is to add that there. Whoops. dense layer count times last neuron power. All right, so here, I'm training with each number of dense layers, and each option for neuron count in the last layer. I train for 50 epochs. Once again, I'm looking for the best model on the train set at this point. Again, we imagine that we can use regularization. Once we find the model that's best on the train set, we can regularize it to make it better on the validation set if necessary. We get the learning curve. We display it. And then in the event that the dense layer count is 0, well, that means we don't have any dense layers. So we're not gonna test every value of every neuron count, because with zero layers, the neuron count is mute. It's mute. Anyway, if you have zero layers, then however many neurons in the last layer is going to be immaterial. Next, we picked out the best model based on the results. It happened to be one dense layer with 64 neurons. And we continue to use the best convolutional block count and filter count, 4 and 32. There's our model. The model associated with those values. Then we train the model. We have early stopping, 25 patients. Again, using the validation loss. And then once we got done training, I think earlier we changed this to the sorted, quote-unquote, sorted data sets. I think that's fine. I don't think that will hurt anything. And so again, the accuracy is really good. 95% on the training set, 91% on the validation set. Just really, really good. And then we have this heat map, which is broken, as I have mentioned before. What is this? Not sure why I didn't display this earlier, but yeah, this is the learning curve for the best dense model. The model with the values that we found from tuning. Interesting. What's kind of weird is just during this notebook evaluation, all of my learning curves are really bumpy, and bumpier than what I've seen in other other models, other efforts I've made building models. So the next thing that I tried to work on is tuning regularization. Can I use? Yeah, I guess. Wait. Yeah, I can use the float. Okay. Ah, gosh. 0 to 4, 0 to 7. That's not really gonna work. Maybe add? It doesn't really matter, but it doesn't really matter what seed I use as long as it's consistent. So I have so this is how many residual blocks I want to use. Residual blocks. That's not correct, but should be residual layers 0 or 4. If I use 0, then I'm going to have 4 convolutional layers. If I use 4, yeah, this code doesn't look right. This code doesn't look good. But what this is really saying, use 4 convolutional, use 0 means using 4 2D convolutional layers without residual and no residual blocks. Yeah. 0 means using no residual blocks. 4 means using 2 convolutional one. 4 means using 1 residual block, 2 layers, and 2 after 2 convolutional layers. 4 layers total. Okay, so I know what I'm doing here, but I recognize that the variable name is confusing. Okay, so data augmentation. 0 means no data augmentation. 0.1 and 0.2 are augmentation factors. Or 2. Dropout. So data augmentation, like there's like a brightness, and you can increase it or decrease. Brightness can be increased or decreased at random by the data augmentation function. If you use 0.1, or it'll be less. There'll be less of a degree. It's random, so it's plus or minus 0.1, and those are the extrema. But If you use 0.2, then it's plus or minus 0.2. So that means the effect of data augmentation will be the effect of transforming your images will be greater on average. Dropout is the percentage of 0.2, or 0.4 are the percentage of dense neurons that will drop out. Only affects training. So I hope that's clear. But we're going to cycle through these values. We're going to cycle through them, just like what we did before. If all three values are 0, we already did that. That's just saying no regularization. And we've already done that, so we'll just skip that. We're doing quite a few models, so saving one, it won't make a big effect, but it should shave a little bit of time. So each time we build a model, we are passing in the values that we found earlier for the convolutional layers, and we're passing through the model we discovered, the numbers we discovered for the dense layer count and the neuron count, and we are using the same number of convolutional layers. They will either be in the form of residual blocks, or they won't. They'll either be in residual blocks or just as a stack of residual layers. Or it'll be just a stack of convolutional layers like the ones we've already dealt with. And so those are two options. Residual layers are a form of regularization. Data augmentation is the form of regularization, and dropout is as well. I feel like this is probably, I don't feel like this is complex, but I think it seems complex, maybe because I have 3 layers of indentation. Makes things complicated. Makes things seem complicated. So yeah, you build your model, you train your model. Now with this model, with this tuning phase, I felt like it was going to be prohibitively take a prohibitively long time to train by default. So what I did, I shortened, I used early stopping. Actually, I didn't use early stop. Yeah. So I used early stopping this time during the tuning phase. I didn't do that the previous time. And I used an unusually low amount of patience, and I used early stopping on the train and validation loss. So, if I had it to do again, maybe I would not be so restrictive. But the whole point of regularization is to reduce the validation loss, and that did not even begin to happen. The learning curves that I got just don't make a lot of sense. And I don't know, I said I wasn't going to talk about data, at this point. The reason I'm doing so right now is to defend my decision to use early stopping and use such aggressive early stopping. I think even in the short time that I trained these models, it became clear that the regularization was not working. I have some reasons. I have reasons to suspect that this needs to be revisited. That I may have made some incorrect choices in my code, and it may be worth retrying, worth another look. But at the time, based on the code, this decision to use aggressive, low impatience was vindicated by the extreme overfitting that was seen immediately in the training. Now I did try one of the problems. There was an error found in the dense layer dropout rate code. So we redid. Did we redo the testing? To train with a dense dropout. I think that what happened is that 5 residual layers was the best. Residual with 5 layers was the best model I found during regularization tuning. I think that's what happened. And so I tried it with dense dropout. I'm not gonna try that again. I'm going to revert, assuming that I do redo this reevaluate the notebook, and I redo this side quest, quote unquote. I'm just gonna try leaving everything else out. Just try the dense. Try doing dropout in the dense layer and using the other ordinary values. But in any case, so we did that, and we retrained with dropout, and it didn't do any good. That whole side quest thing, I don't know. I think it's kind of shitty. Okay, so the best best model from tuning regularization. I did data augmentation and dense dropout. I did not use residual layers. Okay, and so this is, again, like we've seen before, this is information about the model. This is us training the model. It again, with early stopping, with 25 being the patients, and yeah, this model. How can the accuracy be that low? It's almost like the model knows the right answers and is the right labels and is deliberately putting the wrong labels on each image. 16, even if you just guessed, you should do better than that. I mean, you know, as we talked about earlier, I think that the you know, if you just guessed, if you knew, I don't know, it depends on what you think you know or what you think you know going into it. What is this? Didn't we already do this? Okay, I don't know why this is here. This may have been an error. It looks like we're just training it again in exactly the same way. Oh, well, yeah, now I'm really confused. So we're retrying the dropout rate. And it's overfitting again. So what did we do earlier? What was that thing? Oh. Okay. So this is me. So before we said we tuned the we tuned this is okay. This is something different. I remember now. So earlier we tuned the number of convolutional layers and decided on 4, which is the number of total convolutional layers we used when tuning regularization. That tuning did not turn up anything like good results. So now we want to take a moment to consider whether using 4 layers in our residual blocks, is better than using 4 total convolutional layers. So that side quest did not work, did not turn up any kind of better results. Retrain using the best parameters we found in the tuning did not generate better results. We tried, we fixed a bug, and we retried tuning the dense layer dropout rate. We retried tuning just the dense layer dropout rate. Did I end up using this dictionary? No. So yeah, we retried tuning the dense layer dropout rate. That's, this is why I got confused here. I was getting ahead of myself. So we retried it. We used a number of dropout rates with all the values that we'd already tuned, and ordinary early stopping with 25 patients, and just got junk. Just, our models, they all overfit, and just to an extreme level. So our best model was the dense model. And we got a confusion matrix for the dense model on the test set, and just wonderful. Well, again, you can see the report. We looked at errors. So this is, I think I mentioned that I had a function that I wrote to display errors. Maybe I should stop. Maybe I should have stopped by now. Okay, we'll stop, and the next video should be pretty short. We'll be back.